Hello everyone, my name is Han Shengxiang, and this is question 2 of the homework 11 in the probability and stochastic process course. And in this question, at first there are three functions of the FV, and the FV we want to prove that if it could represent the autocorrelation function of a Y-sense stationary stochastic process when the V is equals to tau, and if it could represent the spectral density function when the V is equals to omega. And for this one, at first, the function is Fv is equals to e to the power of minus absolute V. And for this function, at first, before that, we need to know if autocorrelation function R tau is a Y-sense stationary stochastic process. It's a real and WSS stochastic process, and the xt we want to prove if it is this function, so the xt is even and the R tau is smaller or equals to R0, and so it is its Fourier transform of R tau, so the is non-negative, so the Sx is negative, non-negative. So if it's the power spectrum of a Y-sense station process of X, so the S omega is non-negative, is also the non-negative. At first, for this question A, this function is equals to the e to the power of minus absolute V, and at first we want to know that this function is smaller or equal to the R0. R0 is equal, if it is the autocorrelation function, we could put the V to is equals to tau, and is smaller or equals to the R0 is it is obvious, and this function is, we could use the Fourier transform of it is equals to the 2 times 1 and the 1 plus the omega to the power of 2, and it is obvious non-negative, so it is the autocorrelation of a WSS stochastic process, and it's 1, and for the 2, could it represent the spectral density function, and when we could put the tau is equals to omega, and for this the function of the spectrum density function is bigger and equals to 0. It's obvious the exponent function is bigger and equals to 0, so it could represent the spectrum density function. And for the function B, the Fv is sine to the power of 2 over the V to the power of 2, and for this it's like the sinc function is like this one. It's a Fourier transform from its Fourier transform is a triangle wave, and at first we want to prove that it could represent an autocorrelation function of the WSS stochastic process, and for when the V is equals to tau and the sine to the power of 2 over the tau to the power of 2, and is smaller or equals to limit when the tau is access to 0 and the sine to the power of 2 over the tau 2 is equals to 1. And so it is, we could know that it is obvious access it, and the Fourier transform of it is obvious bigger and equals to 0, so it's non-negative. So this function could represent the autocorrelation of the function with the WSS stochastic process xt, and for the 2 we would represent its spectral density function, and when the v is equals to omega, and the sine to the power of 2 omega to the power of 2 is obvious bigger or equals to 0, because it's it's not this, it's a sinc to the power of 2, not the sinc function. The sinc function is this, and so the sinc to the power of 2 is this function, this graph, and so it is non-negative, and it could represent the power spectral density function. And for the third formulas, the formula C is equals to a door function wave, you know, it is this like the door from minus alpha to alpha 1, the fv and the v. And at first, if the door function we want to compute that the door function, the Fourier transform of a door function is the sinc function I have speak above. It's this one. So it is not non-negative. So for the first, it cannot represent the autocorrelation function because it is obvious have the negative value. And for the 2, the spectral, if it could represent the power spectrum, because the function is obvious bigger and equals to 0, so it could represent the power spectral density function. That's all. Thank you.